We can calculate the equilibrium constant from concentrations which are found experimentally, either for the concentrations of aqueous solutions or for partial pressure of gases for the reactants and products whenever they are at equilibrium. So let's look at this reaction. The dinitrogen tetroxide is changed into 2 moles of nitrogen dioxide gas, both of them in the gaseous state. And let's say we will make an experiment and this will come to an equilibrium. And when the temperature is 100 degrees Celsius, we'll be measuring the concentrations of the two gases in equilibrium state. So to find the equilibrium constant Kc for this reaction at this temperature, we first need to write the equilibrium constant expression. So we can write the equilibrium constant expression by using the balanced equation. We start by writing the equilibrium constant, which is Kc, and then we are dealing with the concentrations. We put the concentrations of the products over the reactants. So we'll put N₂, and since it has a coefficient of 2, it will be to the power of 2, as we learned in the last video. Then, since there is a coefficient of 2 in front of 2, again we'll put power 2. This is a concentration of O2 raised to the second power divided by the concentration of reactant, which is N₂O₄, again between brackets, and this is raised to the first power because the coefficient here is 1. Then we will put the concentrations that we found at the equilibrium. So the concentration of NO2 is 0.0172, and this has to be squared since it is squared here. And then we'll divide this by the concentration of N₂O₄, which put the number, which is, let's put the number, which is 0.00140, and we will try to make the division, so we'll get the value equal to 0.211. This is at 100 degrees Celsius, and it's always important to put the temperature here because the temperature is having a fixed Kc. So if you change the temperature, the value of the Kc or the equilibrium constant will be different. It's also important to note that the equilibrium constant doesn't have any units. So I'll just say 0.211 at 100 degrees Celsius for this particular reaction. And let's try to calculate the equilibrium constant for another reaction. In this reaction, the carbon dioxide reacts with hydrogen to form carbon monoxide and water. Since everything is in gaseous state, we will be making the Kp here, but just for a note, because some students asked, can I put Kc or Kp for the pressure? Yes, if you are giving concentrations, you will be putting Kc. If you are giving pressures, you will be putting Kp, and this is for gases, but for solutions, aqueous solutions, there is only Kc possible. So instead of calculating Kc here, we'll be calculating Kp as requested for the pressures. We're trying to find the Kp at this temperature, which is 500 Kelvin, for example. Because we don't have the concentrations at the equilibrium, and we must only calculate Kc or Kp by the equilibrium concentrations, we'll try to make some table, which is called an ice table. The ice table is done only, and ice, by the way, is just a summary for the 3 letters initial and change and equilibrium. So this stands for initial, I for initial, C for the change that happened, and equilibrium is E, and I'm going to tell you how to find out every one of these. The use for ice table is when you are giving the concentrations initially only, but you cannot use these concentrations to find the Kp because Kp only, or the pressures as the Kp only, is found by the pressures or the concentrations at equilibrium. That's why you use this table. So if you are giving the initial pressure of this one as 4.10 and this is as 1.80, but here the concentration of this one is 0, and when you started there was 3.20 moles of, or 3.20 pressure for the water vapor gas already. So let's see how we are going to use the ice table to find this one. Since we didn't add any carbon monoxide at the beginning, the initial partial pressure of it would be zero. After the reaction comes to equilibrium, we measure the partial pressure of water and we find that it is 3.40, but we don't have the other values. So we have four values for the initial pressures at the beginning, and we have only one value for the pressure of water vapor at equilibrium. So that's why we have 3.40 in the equilibrium here, in the equilibrium part here, but we don't have the others. So I will make the ice table like that. I will put the pressures of every one of them under its substance in the row of the initial, and I will put this 3.40 in the equilibrium row under the water vapor only, since these are all given for us. So I can see that the H2O has increased in partial pressure from 3.20 into 3.40. And 3.20 into 3.40, this is an increase of 0.20. So I can say that this increase is 0.20. And we can say that if I don't know how much is the increase in the rests, because I have only their initial values or the decrease, I can say that if this is equal to 0.20, I would also say that this has decreased by a certain value which I don't know. So let's say that it has decreased by X. But why this one has decreased? Because this is in the reactants. So I will say that this is decreased by a value which I don't know, which is equal to X. And this one has decreased also by a value which I don't know, which is equal to X. Since carbon monoxide is a reactant, is a product, so I will say that it has increased by X. And if you notice that I will always say X here, because the ratio of the reactants to the products in this balanced equation is 1 to 1 to 1 to 1. So if this is 1, this will be 1. While if this was 2, I will put here 2x. So these numbers and the ratio of the unknowns is equivalent to the ratios of the balanced equation. And this one will be also plus x. So I know that now the plus x is equal to 0.20. So this means that the CO2 has decreased by x. So this means that it has decreased by 0.20. If initially it was 4.10, so I will expect it to be 4.10 minus 0.20. So minus 0.20, but how I will know that? Because this is x, and we said x equal to 0.20 from here. And since this is x and this is x, we can write instead of plus x, and we wrote here minus x, so it is minus 0.20. So 4.10, and that's minus 0.20. So the pressure at the equilibrium was equal to 3.90. And on the other side here, this is 1.80 and also decreased by 0.20. So this will come to a pressure of 1.60 at the equilibrium. And this one was 0, but it increased by x. Still, x is all the time equal to 0.20. The only difference in the values here is that it will be plus. This one decreased and this one has increased. So when 0 is added to 0.20, it ends at 0.20. Now I have the equilibrium pressures. So I have had the equilibrium pressures in all the reactants and products. I can see that I have lost some of the reactants and I have gained some of the products. All the values of the pressure has decreased in the reactants and increased in the products. Now that I know my equilibrium constant expression and I know my pressures, I can just write Kp is equal to the product's pressure, which is CO pressure, multiplied by pressure of water, and divide this by the pressure of the reactants. So I will say the pressure of CO2 multiplied by the pressure of the hydrogen gas. And since all these values are known already, we can just put the numbers now. So I will say that the pressure of CO, and don't take the numbers from the initial, that's why we made the table, so that we can find the partial pressures at the equilibrium only. So that's P of the CO, pressure of the CO is equal to 0.20, and that's multiplied by the pressure of water at the equilibrium, which is 3.40, and then we'll divide this by the pressure of the CO2 at equilibrium only. Don't use 4.10, this is initial, but here we'll use 3.90. So I'll say 3.90, and this is multiplied by 1.60, which is the pressure of the hydrogen gas at equilibrium. And then the rest will be with the calculator to find the partial pressure, or sorry, the Kp to 0.11 at 500 Kelvin, and as we said, has no unit.